Hello and welcome. Today we are going to be talking about motion, distance, displacement, and how we graph it specifically. So, what is motion? We care about three main things right now. The position of something, which is just the separation between an object and a reference point. Where are you in relation to your refrigerator? Or how far an object is from the origin, more broadly. The distance doesn't need a reference point. How much ground has an object covered during its motion? How far do you have to walk to get to school? Is it a mile? Is it 20 feet? And displacement is the change in position of an object. Remember that this triangle is the Greek letter delta, and we use it to mean change. So delta D is change in position. D is what we use for the position. So displacement is the separation between two objects and the direction. For distance, the direction doesn't matter. You walk 2 miles. It doesn't matter what direction you went. Displacement, the direction does matter. So you can see down here, I've got the distance that I walked is this long, windy path, but my displacement is how far am I from the starting point? Not how far did I walk, how far am I from the starting point? Displacement is the change in position of an object, the distance and the direction. And like I said, it's normally denoted by this delta D. And you find it by doing your second position minus your first position, or your final position minus your initial position. These subscripts, the 2, 1, F, and I, are just things that we use to specify what we're talking about. So this little F means the final position. The little I means the initial position, just so that we can keep it all clear. In this class, in physics, typically forward or right or up is the positive direction, and left or down or backwards is the negative direction. So if somebody is walking backwards from the origin, they would have a negative displacement. If they are walking to the right from the origin, they would have a positive displacement. So let's look at an example. I've got a lizard that's starting out at 25 centimeters and moving to 85 centimeters. What distance does this lizard travel? And what is the lizard's displacement? Hopefully you said he traveled 60 centimeters moving forward, and his displacement was 60 centimeters to the right. Remember, displacement, direction matters. So he moved 60 centimeters to the right. Check out these examples. What is the distance and the displacement of the ball in each scenario? So in the first one, in the top left, we've got it starting at about 10 centimeters and ending at 80. So this ball, I do 80 minus 10, final minus initial, to get that the ball has moved 70 centimeters. Distance and displacement is going to be 70 centimeters to the right. This second example in the top right, I'm starting at 15 centimeters and ending at 1. At 0. So my final minus my initial is going to be negative 15. For distance, I just moved 15 centimeters, but my displacement, I moved 15 centimeters to the left. In this third example, in the bottom left, I start at negative 10 and I move forward to 6. So my distance is going to be 16 centimeters. My displacement is going to be 16 centimeters to the right. And in this last example, I started at negative 10, I end at negative 20. So my distance will be 10 centimeters and my displacement will be 10 centimeters to the left. Will distance and displacement always be the same number? What do you think? So here's an example where I've got a hiker that travels 8 miles east and then 5 miles north. What distance has the hiker traveled and what's his displacement? His distance traveled is going to be 8 miles plus 5 miles, which will give me 13 miles. His displacement is this diagonal arrow. It is the direct path between his origin and his current location. How far is he from the origin right now? And that's going to be like 9.43 miles. So his displacement up and to the right, or east and north, is going to be smaller than the full distance he traveled. He traveled 13 miles, but his displacement is only 9.4 miles to the northeast. Here are a couple more examples that you should try. A car moves 65 miles due east, then 45 miles due west. What distance has the car traveled, and what is the car's displacement? So it starts here, it moves 65 east and then 45 west. What is the distance and the displacement? The distance is 110 kilometers total, but the displacement is only 20 kilometers to the east. Then we've got this second example where we've got Ned Naylor walking 5 blocks north, then 7 blocks east, 8 blocks south, 3 blocks west, and 3 blocks north, and is very tired at the end. What distance has he walked and what displacement has he walked? I find it really useful on a question like this to try sketching it out. So if I start at this point, walk 5 blocks north, 7 blocks east, then 8 blocks south, 3 blocks west, and then 3 blocks north. So I'm ending up right at the center here. I started over here at this side. So my distance in total, Ned walked 26 blocks. But the displacement, he ended up only 4 blocks east from where he started. Remember that you always have to include your units. How many kilometers or blocks was it? Just saying the distance is 26 doesn't mean much. And remember, when you're talking about displacement, the direction matters. So is it east? Is it south? Is it to the left? Is it up? What is the direction? Lastly, we can graph motion, and we can look at a graph to tell a lot about what was going on in a situation. There are 2 main kinds of motion graphs: position versus time and velocity versus time. Next class is going to be all about velocity and velocity graphs. So today we're just focusing on position graphs. A position graph shows you the position, typically in meters, away from a starting point, which is going to be the origin, which is 0 meters in this case. And it'll show you how long it took to get to that position. A single point on the graph shows you how far you are from the starting position and how long it took you to get there. An important thing to know about these position and time graphs, I know we just learned about lines of best fit where we told you specifically do not connect the dots. This is a different kind of graph. These aren't lines of best fit, and so you are connecting the dots. So we can see we've got position on the y-axis and time on the x-axis. Remember your units. In this example, it's going to be meters and seconds, and that is often what it will be, but it doesn't have to be. You could have miles per minute or inches per, don't do inches, we don't use standard, we're using SI. So centimeters per hour if it's a snail moving along. So let's break this graph down. The circled area here in orange shows what motion looks like on a graph when you are moving forward or in the positive direction. Each point tells me how long it takes to get somewhere, and I've got a positive displacement, a positive distance. So after 5 seconds, I have moved 1 meter forward. After 10 seconds, I have moved a total of 2 meters forward. That is what moving forward or in the positive direction looks like on these motion time graphs or position time graphs. When you're standing still, it'll be a straight horizontal line. This object is not moving. And I can tell that because for 10 seconds, between 10, 15, and 20, the object is still always at 2 meters. It does not matter what is going on in these 10 seconds. The object has not moved. It is standing still at 2 meters. We can also see what it looks like to move backwards or in the negative direction. This object started at 20 seconds. At this point, it is 2 meters away from the origin. So it takes 5 seconds to move backwards 2 meters. And now we're back at the starting point. Then I'm going to keep going backwards beyond the starting point for another 10 seconds and end up 4 meters behind the starting point. So maybe this is just walking forward and backward. It took me 10 seconds to walk forward 2 meters. I stood there for 10 seconds. I walked backwards back to my starting point in 5 seconds. And then I kept going backwards 4 meters behind my starting point. And it took me 10 seconds to do that. And then you can see here, we've got another flat line. So it's another not moving. You can use a graph like this to tell a story, or you could take a story and put it on a graph like this. So for example, I got up from my desk and walked the 2 meters to my door in 10 seconds. I opened the door and my dog couldn't decide if he wanted to be in or outside of the room, so I just stood there at the door for 10 seconds. Afterwards, I walked back to my desk and it took me 5 seconds to get there, and then it took me 10 seconds to walk the 4 meters behind my desk to get to the couch. And then I started sitting on the couch and I did not move. So that's an example of a story that you could tell from a motion graph. You could also go the other way. From a story, you can draw the graph. And that's going to be the stuff that we are practicing with next. Bye-bye.